A very good evening and a very warm welcome to this live streaming session where we interact with our participants in this NPTEL course on digital signal processing and its application. As you know, we have a couple of these live sessions, live interactions with the instructor and the teaching associates. And I'm very happy this evening also to be accompanied by my teaching associates, whom I'll introduce shortly. And we look forward to your coming forward with your questions, your queries, anything that you would like to share in terms of how you've been engaging with this course, or anything else that you would like us to answer or to comment upon in what you've been learning. So with this brief introduction, I now invite the viewers to introduce themselves and pose whatever questions, doubts, any comments that you have, and so on and so forth. Yeah, so now we'll wait for you to come forward with your... First, maybe, you can tell us, I see that there are a few viewers who are already in this session. So you could introduce yourselves and then you could start putting your queries and you can share your thoughts with us. So once again, I welcome the participants who are in this session. I guess they will keep joining slowly. Yes, I'm very happy to see a comment, or rather maybe you can say a question from Shankar R. And the question, let me explain what his question is. His question is, why are we saying that x of 2t is a compressed version of xt? So, you have a signal xt, and when you write x of 2t, you are essentially referring to a signal which has been compressed by a factor of 2 on the independent variable. Why is this so? Or can one explain why replacing t by 2t amounts to compression? Well, let me explain to you with some specific points. So let me start sharing. Yeah. Now, I suppose that you're able to see my whiteboard. Can you confirm, Shankar, that you're able to see my whiteboard? All right. So now let me start writing. You see, x of t. Let's assume x of t looks like this. So let's assume that x of t is like a triangular function, which is going from -1 to +1. Okay. Now, you can see that x of t goes to 0 at t equal to 1. Is that right? So x of t goes to 0 from 1 at t equal to 1 and -1, plus -1. Okay. Now, if you take yt equal to x of 2t, okay, so yt, you see, yt would go to 0, would go linearly from 1 to 0 when x of, well, yt equal to x of 2t, okay? So 2t goes from 1 to 0. Now, 2t goes from 0 to ±1. I'm sorry. Okay. So which means t goes from 0 to ±½ So compare this, okay, and this, the original signal xt. This is xt, and this is x of 2t, which is yt. So you see that x of 2t is a compressed on the independent variable. It's a compressed version of xt, compressed on the independent variable. You see, you must understand it this way, that when you multiply the independent variable by a constant, if the constant is greater than 1, you're essentially speeding up the process of moving through the continuum of values. Now, if you speed up the movement in the independent variable, you are compressing the signal, and vice versa. If you replace t by 2, then you're stretching the independent variable, and therefore you are expanding the signal. So is that clear, Shankar? Can you respond on the chat? And while Shankar responds, well, let me, just for clarity, let me also draw x of t by 2. So so let's have So is that clear, Shankar? Okay, so I see that there is one more participant, Garvit, right? So Garvit, welcome. Shankar, is the idea clear to you? And meanwhile, Garvit can introduce himself and share any questions or queries that he might have. And while you do that, I'm now going to have my two teaching associates flank me on either side. So maybe, yeah, yeah, you can, or maybe we can do it this way. Yeah, you can come, you pull up these two chairs. I can move one chair there. The other chair can be moved here. Right. And, yeah, move that. So, yeah, Mrinal, you can come this way. And I wish you can sit there. And yeah, come. And I'd like to, while you respond, yeah, I think Shankar has understood. Garvit, yeah. So that we can see both of you. Ayush. I'll step a little behind, so both of all the three of us will be visible. So, yes, so I'm very happy to introduce my two teaching associates. I believe that they have been interacting with you on the discussion forum. So I have Ayushi Barve on this side, and I have Mrinal Saure on this side. And maybe you should introduce yourselves. Yeah, come a little bit forward and introduce yourself.
Right. So I am Ayushi Parve. I'm currently a final year undergraduate student in the Department of Mechanical Engineering at IIT Bombay.
Yes, Mrinal can be seen. Yes.
Hi, I'm Rinal Shaurya and I'm a fourth year dual degree student from Electrical Engineering Department at IIT Bombay. And it was a really good experience to be a teaching associate for this course.
So Ayushi and Mrinal have been teaching associates in this course. They have been carefully reviewing the assignments and whatever you've been putting on the discussion forum, and they've been trying to respond to your queries. And in fact, they're here today because, this would be the last interactive, we understand that your final examination will be coming up soon in the course. And it's unlikely that we'll have an interaction session before the final exam. We can't have an interaction session now. So this would be a chance for them to be introduced to you on the same interaction session. So now we look forward to more questions and inputs from you. I can see that Shankar is satisfied with the explanation. And now we're looking forward to more questions from you or anything that you'd like to share with us. I hope you can hear us clearly and see us clearly, see us properly. Yes. So Garvit and Shankar, any other viewers? Yeah, I see. Inilaya Singh, Shankar is asking Inilaya Singh why that negative mirror is coming. Okay. Now, Shankar, there is nothing negative and positive about these frequencies. Let's explain that. This is the first thing that we must appreciate. So the first thing that we have to appreciate is that, every sinusoid, see, you're thinking in the Fourier transform, essentially you're thinking of a signal as a linear combination of sinusoids. Or in fact, if it's a Fourier transform for real signal, then you're thinking of it as a linear combination of sinusoids. Right, of the form cos omega naught t plus phi naught with an amplitude of a naught. Now, you see, the point that we must appreciate is that every such sinusoid is really two oppositely rotating complex numbers. So this is here you're rotating clockwise, rather anti-clockwise. And this one rotates clockwise. So each sinusoid is really a linear combination of two oppositely rotating complex numbers with the same amplitude equal to half the amplitude of the sinusoid, opposite phase, right? The one rotating anti-clockwise has a phase which is the same as the sinusoid, and the one rotating clockwise has the negative of that phase. And therefore, the so-called positive and negative frequencies are really the angular frequencies of rotation of these two complex numbers, two phasors. Each sinusoid has two phasors embedded in it. So you should not give any special significance to the positive frequency or to the negative frequency. Both of them in that sense are, surreal or imaginary. Both of them are equally important for bringing the sinusoid into existence. Now, we tend to be comfortable with the idea of positive frequency because we associate it with the frequency of the sinusoid. But every sinusoid, you must remember, has these two oppositely rotating complex numbers which come together to create it. And the frequency that you talk about in the Fourier transform, so let us write the expression for the Fourier transform. The Fourier transform of xt which we could write as capital X j omega as a function of the angular frequency, capital omega. Now let's understand this expression. This is like an inner product, a dot product. You can think of it as a dot product of xt with e raised to the power j omega t. So what are you doing here? You're finding out the component of xt along the phasor rotating with an angular velocity of capital omega. Now, capital omega takes all the values going from minus to plus infinity. Because the sinusoid takes all frequencies from 0 to infinity. So your question relates to, why we bring a negative. Where is this negative mirror coming from? Now that negative mirror is nothing special in aliasing. In any representation in terms of phasors for real signals, you're going to have symmetry in the magnitude. The magnitude of the Fourier transform is going to be an even function of the angular frequency. And the phase of the Fourier transform is going to be an odd function of the angular frequency, because you saw that every sinusoid has two oppositely rotating phasors with the same amplitude and opposite starting phase. That's why that, odd symmetry for the phase and even symmetry for the magnitude. All right. And then, of course, a consequence of that is that you take the original spectrum, shift it to every multiple. You see, here you're thinking of complex exponentials, phasors, not sinusoids. Remember this, right? And therefore, you need to think of both the positive and the negative phases. All right. The other way of understanding the same thing, let me explain to you in another way. You see, what are you doing when you alias? When you or when you sample? When we sample, you're multiplying. So sampling amounts to multiplying xt by a uniform train of impulses. So let's say summation k going from minus to plus infinity, delta t minus kts, where ts is the sampling interval. Now, delta, this sum of, this uniform train of impulses which you have here, is a periodic signal. It's periodic with the same period as the sampling interval. Is that right? And therefore, you could expand it in a Fourier series, right? So you could expand it in a Fourier series. So Fourier series of this periodic signal would be of the form summation L going from minus to plus infinity. Remember, you're writing a complex Fourier series here. CL e raised to the power JL. Now the period is TS, so 2 pi by TS T. Is that right? Now it turns out that all the CLs here, all the Fourier series coefficients here, all are equal to 1 by TS. They're the same. And therefore, what you're doing effectively is to multiply xt by this Fourier series. Now take any one product here, xt into any one of the terms. What is it doing? It's taking the spectrum of, you see, it's a modulation. It's a modulation of the original signal with a rotating phasor. And therefore, when you modulate in the time domain, yeah, so let's take the nth term here. It's xt into e raised to the power j. Let me write it as omega lt. And omega L is essentially L times 2 pi by Ts. Now, when you modulate a signal xt with e raised to the power j omega lt, you're shifting the spectrum of xt forward by omega L. Now, if omega L is negative, you're shifting it backwards by mod omega L. And as you can see, you need to have a pair of equal and opposite amplitudes. I mean, equal amplitudes and opposite phases for L and minus L. And therefore, you get the so-called negative, what you're talking about, the negative mirror. So is that clear, Shankar? We hope that this clarified the question. Very good, Shankar. So glad it was clarified. Now we invite more questions, more discussion. Yes, so I hope we have other viewers. So then, we look forward to other questions or other inputs from Shankar or other viewers. Yes. So Shankar, you're saying you gave in class to add sinusoidal signals using trigonometric rules. Okay. Please explain. Well, you see, there are two ways of understanding this. When you're adding sinusoidal signals, of course, here, I believe you're talking about adding two sinusoidal signals of the same angular frequency. Otherwise, it is difficult to use trigonometric rules. We can use them. We can, anyway, let's look at a general trigonometric. I mean, the addition of two phasors would imply that the angular frequency is the same. If the angular frequency is different, it would again result in two phasors, which are multiplied. So you could think of a sum of two phasors also as a product of, if the amplitudes are same. Anyway, let me write down the trigonometry behind it. Now, all this is based on the simple trigonometric idea that you have, see, you can take A cos, all right? A0 cos omega naught t plus phi naught plus A1 cos omega. Now, I'm keeping the same angular frequency here, please note. Now, you can do it in two ways. You can either break this into its complex exponentials and add the two complex exponentials separately, or you could decide to add them by splitting the trigonometry here, right? So you know that cos of A plus B or alpha plus beta can be written as cos alpha cos beta minus sin alpha sin beta. And therefore, we can expand each of them. So you can expand A naught cos omega naught t plus phi naught as A naught cos phi naught times cos omega naught t minus A naught sin phi naught into sin omega naught t. And the same thing can be done for A1 cos omega naught t plus phi 1, whereupon we would get A naught cos omega naught t plus phi naught plus A1 cos omega naught t plus phi 1 would be equal to A naught cos phi naught plus A1 cos phi 1. Now what I'll do is I'll write these in blue and the other one in, let's say, green. So A naught sin phi naught plus A1 sin phi 1. And I'll write the other one in green. Cos omega naught t and minus sin omega naught t. Now you see, you can think of cos omega naught t and sin omega naught t as two perpendicular vectors because they are orthogonal with respect to their time period, isn't it? Now you can combine these two. You can think of this as having a combined amplitude and a combined phase. Is that right? So how do you do that? Well, this is equivalent to, let's say, A2 cos omega naught t plus phi 2, where sin phi 2 by cos phi 2 is equal to A1 sin phi 1 plus A naught sin phi naught divided by A1 cos phi 1 plus A naught cos phi naught. Okay, so this is the angle, the phase. Okay, and the amplitude would take the value in A2 squared is going to be A1 cos phi 1 plus A naught cos phi naught whole squared plus A1 sin phi 1 plus A naught sin phi naught squared. So thus you could find out the amplitude and the phase by using purely trigonometric identities, right? Now, this is where the two sinusoidal components have the same angular frequency. Now let's take a situation where they have the same amplitude but different angular frequencies. Same amplitude but different angular frequencies. So let's take A naught cos, you see, let's say find, well, omega naught t plus phi naught plus the same amplitude. Let's say cos omega 1t plus 5. Now here we can invoke the trigonometric identity cos alpha plus cos beta. All right. So you know that cos alpha plus cos beta can be written in terms of cos alpha plus beta by 2 into cos alpha minus beta by 2. Is that right? So cos alpha plus cos beta is twice cos alpha plus beta by 2 into cos alpha minus beta by 2. And thus, of course, you see that a sum of two sinusoids of the same amplitude is also equivalent to a product of two sinusoids. Right? So I hope that is what you had in mind when you asked me to explain the trigonometric rules. Right? Now, of course, the same conclusions can be drawn by decomposing the sinusoids into phasors. In fact, perhaps it's easier to do that at times because, you can work with the underlying complex numbers, and that makes the arithmetic neater. So sometimes it's easier to go into the phasor domain. In fact, the movement to complex numbers is essentially to ease your computation, not to make it more complicated. Right? So is that right, Shankar? If you understood this, or any other questions that you have? In fact, we also invite the other participants, the other viewers on the channel just now, to pose any comments or queries that you have. Okay, so you've understood and you're asking. Shankar is asking, harmonics is also addition of different frequency. Yes, that is right. Well, harmonics is definitely the addition. See, when you say harmonics, then the frequencies are rationally related. So the frequencies of the harmonics are rational multiples of one another. And that means they're all multiples of a fundamental frequency. Right? So harmonics is a special case of combination of sinusoid. That should be clear. On the other hand, you could be combining two sinusoids which are irrationally related as well. They don't have to be harmonics. When you say harmonics, you are implying that both of them are rationally related. The ratio of the frequencies is rational. And yes, if they have the same amplitude, then you could think of it again. So sum of two harmonics with the same amplitude amounts to a product also of two sinusoids. So in fact, you see, what it really means is that when you have two sinusoids of the same amplitude being added, it's like an amplitude modulated signal with a carrier and a message. The carrier is the middle frequency, the average of the two frequencies. And the message has a frequency which is half of the difference between the frequencies. So you're viewing, that's another way to understand this. When you look at a sum of two sinusoids of the same amplitude as a product of two sinusoids, then you're thinking of it as a carrier modulated by a message, amplitude modulated by a message. The further questions, comments from the audience? So I hope many of you should have been up to date with the assignments and are able to solve the assignment questions and understand the lectures. I'm hoping that some of you have tried, although we have not mandated it as a part of the course, I'm hoping that some of you may have tried to actually design some filters based on what you've learned, IR filters, FIR filters, based on what you've learned by ascribing certain specifications, reasonable specifications, and trying to realize the filter with those specifications. Unfortunately, we haven't been able to orchestrate an assignment of that kind. But, I hope that many of you must have tried that yourself. So any further questions? Or anything else that any of the participants would like to share? In the absence of which we could then close the session. Let me pose a couple of questions to the people who are still in the session. How many of you would have, understood more than 80% of what you listen to in the lectures? Thank you. Yes, thank you, Shankar. How many of you would have understood more than 80% of what you listen to in the lectures? We have 4 concurrent viewers right now. So Garvit also seems to have. So Garvit, do you have any questions or anybody else who's in the session just now? All right, so then if there are no further questions, then we will bring this session to an end, right? And thank you so much for participating. And we hope that, you have learned and benefited from this course. Yeah.